Hello, everyone, and welcome to the Reprogram Podcast. I'm your host, Dr. George Murphy. Our guest today is Dr. Rozalyn Anderson. Dr. Anderson is professor of gerontology and geriatrics and the director of the Metabolism of Aging program at the University of Wisconsin School of Medicine and Public Health. Dr. Anderson's research focuses on understanding interconnections between nutrition, metabolism, health, and longevity. Among many other things, she and her group have made seminal findings in understanding caloric restriction and how it delays or offsets the onset of aging-related disease. I hope you enjoyed today's discussion, and remember, knowledge is power. Dr. Anderson, it's fantastic to have you on the podcast. Welcome.
Thank you. It's lovely to be here.
So I always like to start out with everyone's origin story. So if you could tell us a little bit about yourself and maybe how you became interested in aging and caloric restriction, that'd be fantastic.
Yeah, well, I suppose it's kind of a wandering tale. And I think, this is good for trainees if they're listening. There's no one path to wherever you're going to go. There are many ways to the destination. I started out working in yeast, actually, in cell cycle. And then I moved to the United States in 2000. Where I joined a yeast lab, but it was a yeast aging lab. So that's when I started becoming interested in aging. My background is in biochemistry, and I had the awesome power of yeast genetics. And so taking on something as complex as the aging process in such a simple organism was like, boy, can we really do this? So I had a wonderful postdoc in Boston area, and we were really interested in metabolism. So we were able to change the pace of aging in yeast simply by tweaking metabolism. And we actually discovered the mammalian components of the NAD salvage pathway. So it was a heady time and just wonderful stuff. And so at that time, then I was, thinking, okay, this caloric restriction gig's pretty interesting. And I was like, wait a minute, there are mice on caloric restriction. I know I was a bit late to the game on that one. So I moved to Wisconsin to work with Richard Weindruck. And he had a whole project looking at mice. He actually had a company looking at, factors that promote longevity at the time, one of the first, I think. And so I was working there, and we had converted from yeast to mice, which was a bit of an uphill. Brilliant, really, really fun. It's metabolism. The message was still there. And then I discovered, hang on a second, there are monkeys on caloric restriction. So I stayed in Wisconsin and joined that program. So this was a really ambitious it ended up being over 30 years, a longitudinal study of aging and caloric restriction in rhesus macaque. And so I became more and more involved in that. And it's been actually a big chunk of my career now, trying to understand what is going on during aging that creates disease vulnerability and what is different about the animals who are caloric restricted. Why is their aging different? And so that's the nutshell.
Perfect segue. So caloric restriction is fascinating, and it really is, for us in the aging world, the gold standard for everything we compare everything else to. Maybe potential interventions or novel geroprotectors. How does it compare to sort of what you see with caloric restriction? So if you would, as an expert, can you define caloric restriction, and more specifically, what are the molecular underpinnings of caloric restriction that allows an individual that's restricted in this way to sort of, delay aging onset?
Okay, so the first thing, nobody actually knows how caloric restriction works.
Perfect.
We just know that it does. And it's like, this stuff is old as dirt. And in the early days, over 100 years, it was more like observation and phenomenology. And then, as you move through time, the physiology became important. But then with the dawn of genetic techniques in short-lived animals, we were able to see that caloric restriction worked in those. The initial observations were in rodents. And so now you could bring that genetic tractability, drug screens, mutation screens, all of this stuff to try to understand what's happening. And then now revisiting in mice, monkeys, and persons on caloric restriction, we look for those clues. So in my own completely and utterly biased opinion, it's metabolism. I happen to think that energy itself is information. And so the energetic setting of a cell, a tissue, an organism pretty much defines the suite of behaviors or processes that are available to it. The energy has to be matched with the function. And so is a cell dividing? Is it not dividing? Is it quiescent? Is it going through differentiation? All of these programs have to be energetically matched. So I think what happens with caloric restriction is this imposition of a very efficient stringently regulated metabolism, like metabolic setting,
Sure.
that is more resilient in the long run. So that integrity of metabolic processes and the signaling to the cell, this is the state of us now, sort of thing, that's maintained because it's all strapped into a particular program of efficiency first. And I think that's what really drives it. But, you've heard of the hallmarks of aging.
Sure.
There are many. And so everyone has their own favorite process to explain what goes wrong during aging that creates disease vulnerability. But I think, I happen to think that it's really a combination of all these things. We're only looking them as individual fields, but it's all one thing. It's the integrity of cell biology. So, yeah.
Wonderful, wonderful. And the integration of all systems coming together to promote aging or lack thereof brings me to my next question, which is, obviously, we have these wonderful models that we can study aging biology, and we have worms, we have mice. You just sort of outlined all of these rhesus macaques, non-human primates, things of that nature. I think the interesting thing about caloric restriction is that we can also test it in humans, right? With other maybe geroprotectors being much more difficult, harder to run clinical trial.
Yeah.
So how does sort of the discoveries, or how do the discoveries that you've made, as you noted earlier on in your career, in mice or in worms or things of this nature, or even yeast, right? How do you try those in the human condition? And how does that relate to, nutrition and metabolism? Are we what we eat? So how do you sort of roll all these things together in humans to try to understand what is the impact of caloric restriction and how do you study it in us?
So first and foremost, we are what we eat. We are regenerating parts of us all the time. I mean, our neurons are the ones we got, by and large, but all other cell types, there's repair, they're retired and replaced by new ones. Stem cells, of course, your own favorite place to be. So we are exactly what we eat. Our cells are made from the building blocks that we ingest as part of our diet. I think when it comes to the idea of looking in humans, there's a wonderful trial called Caloric that was set up by NIH, NIA, at 3 different sites, 2 years of caloric restriction. And, what's beautiful about it is that what we see in our monkeys, where we know we have health and survival benefits, is what is observed in the humans. And that is also aligned with what has been long known in mice and rats. It comes down to this metabolism, as I said, this maintenance of metabolic integrity. And this is the same message that you'll see if you go to flies, worms, yeast, it's all there. So I think that component, as you go in increased complexity, so in a worm, for example, less than 1,000 cells, beautiful genetics and clues that you can glean, the key is look at those most conserved features. Energetics is the oldest of all. It is totally conserved. The way metabolism works, those communication networks are totally conserved. So you may find differences in the actual specifics, this drug, that receptor, PK, PD, but the fundamental biology, it's all there. And I think that's what is harnessed by caloric restriction.
Fantastic. And so as we've discussed, caloric restriction may be the gold standard of what we're looking for. And as you've highlighted, we don't really understand how it actually works, at least molecularly. But also, as you've highlighted, we understand maybe what the signatures are, what the molecular signatures and sort of what are the markers or indicators to look for. In your estimation, is there anything on the same level of caloric restriction? So if we look across potential geroprotectors, which people are interested in, if you think of something like rapamycin or maybe even other novel sort of indications, is there anything that in your mind gives you the same sort of impact that caloric restriction does? Sure.
Yeah, so I think rapamycin is the front runner right now. There's a lot of evidence from yeast, worms, flies, mice. And you may not be aware, but I'm involved in the dog aging project, which has now moved its location here to the Boston area at Tufts, although it's a national program. Within that, there was the test of rapamycin in aging dogs. And so I'm involved in that program now as well. So I can tell you that I have colleagues and friends involved in clinical trials of rapamycin. And so it's the most promising thing, I think, to come out of the ITP. And importantly, it works in males and females. So the ITP is the Interventions Testing Program, another stellar NIH, NIA-sponsored program. And they test drugs to see if they can see a longevity effect in these genetically diverse mice. So rapamycin emerged from there, and it's pretty robust. Early ideas were, this is going to compromise metabolism. There were some hints that there would be some glucoregulatory impairment. Turns out that this can be tweaked by getting the dose right. So the dose is not what you would use as an immunosuppressant. It's about 1/5 that amount. And then the dose frequency is not the same. So you seem to be able to just target in on those mTOR, target of rapamycin, regulated processes just enough to tweak the system without incurring those side effects. And so that is looking very promising. Of all the agents out there, but there's others. The alpha ketoglutarate story is pretty cool. There are, the senolytic story, super interesting. So that's targeting specifically senescent cells, or as I think they might call in the public, zombie cells.
Yes,
which is very visually good. So that's a very interesting idea of just going in a one swoop and removing some of the elements that are creating damage and causing problems. And so you go in, sweep those away, and then wait for, a year or so, and then do another round later. And so we're learning so much about what create problems to precipitate disease vulnerability. And so these strategies go in there. So the senolytics, I think, are very, very interesting. Rapamycin as a, gerotherapeutic, I think has the most data behind it right now and the most promise. But that doesn't mean to say we're not on the brink of a whole bunch of other compounds. I know it's hugely active area of research.
Wonderful. So we are big fans of Rich Miller and the interventions testing program. In the podcast notes, I'll put the link for the ITP in case anyone's interested. There, obviously, you have this really elegant model of genetically diverse mice in which you can test for the duration of the mouse life, all of these potential novel gerotherapeutics. I think one of the things that we're trying to do is apply sort of human stem cell-based models to try to understand how these things might dynamically work in a human system, which is difficult. So can you share with us your thoughts as far as you talked about energetics or maybe mitochondrial activity? If you were sort of designing a trial in which you were looking at the efficacy of a novel geroprotector, and obviously you can't wait, the 80 to 100 years of life to see if something's effective, what are the signatures that you would primarily look for to tell whether or not something is working?
Yeah. Well, I think, you'd probably start with, clinical indices, so risk factors, biomarkers, but one of the things about these are things that inform about disease conditions. They're not really purposed to aging, by the way.
Sure.
Another element that is very popular at the moment is looking at methylation clocks. So these are little modifications on the genome that change over chronological age, which is the timing of age, but seem to be offset by what's called biological age. So somebody who appears younger than they actually are should have a younger methylation clock. So that's another tool that could be used. In the clinical realms, I think people are much more interested in functional outcomes. So things like grip strength and gait speed are amazing predictors of future morbidity or comorbidity or polymorbidity. And so I think the solution is going to be recognizing that people are an entire entity comprised of tissues, systems, cells. And I think when you bring in each of those different metrics that operate at different scales, by integrating those, I think you'll have the best bet. But here's the problem. You take some middle-aged people, they're healthy, they have no problems, they can run up the stairs. What do you measure in these folks, right? They don't have disease risk. So I think that true biological age index is still eluding us. I think we're close with the methylation clocks, but that connection to biological age is still, we've more to learn there.
Yes.
But I expect it's right on the horizon. There's so much exciting stuff coming out at the moment in this field.
Yes, as we've discussed, we're huge fans of biological aging clocks, and we use that in our work, trying to sort of repurpose them sort of in stem cell-based models. If you look at a Rich Miller, not a big fan of biological aging clocks, he prefers ARIs or aging rate indicators. Yeah. At any given point in time, maybe he would say you can sort of see what your rate of aging is, but if you're trying to look longitudinally, that's maybe a bridge too far. I guess something we struggle with all the time is what actually is a geroprotector? And also, what is a longevity signature, right? So in the context of disease, if you have improvement of Alzheimer's disease and related dementia, is that a geroprotector? or do you need a basal background of overall health and have
Yeah.
improvement of performance there? So do you have a definition of geroprotection that's connected to
Yeah.
improvement of disease, or what is your definition and longevity signature sort of, I guess, indicator of?
Yeah. And so, well, this gets to a very hairy eyeball, right?
Sure.
What is aging?
Yep.
We seldom can describe it in the absence of incidents of age-related disease, right? And so a lot of the time when we're talking about aging or gerotherapeutics, we're not all talking about the same thing. It's a language issue. I think we need much greater dissection, hair splitting, which as scientists, of course, we love to do.
Yes.
So I think, if you were interested in something that was going to offset age-related conditions, you'd start with those. And then the idea would be that this agent is geroprotective. So you could imagine a person who's, for example, overweight with metabolic syndrome. In that context, metformin will be geroprotective. It's pretty clear. The data are out there. It's really obvious. If you've got somebody who's, in their 70s, cognitive decline, now you're going to focus in on, brain neuroprotective measures. Although we focus a lot on neurons, we should really give some love to the glia.
Yes.
Brains aren't just neurons, and of course the vasculature as well. So I think we still need a better language to dissect these things out. And as we have successes in different disease conditions, we'll be able to refine how we talk about these things. But in umbrella term, gerotherapeutic and geroprotective is an agent that's going to offset the timing of that first morbidity, whether it's cardiovascular disease, metabolic syndrome, neurodegenerative disease, all of these things. And that's what we're looking for. We're still best served looking for these things in animal models where lifespan is short and full medical knowledge is known and the environment is completely controlled. So one of the things we don't do so well in bench research is the exposome, right? So life experience, early adverse events, nutrition, exposures. And I think the dog aging project is going to really do some damage there because these are companion dogs living in the environment
love the
with
idea.
their
Yeah.
owners. And there's a whole branch within DAP that's looking at exposome. So you'll bring genetics, huge diversity in the dogs, exposure and complete differences in environment where they're raised, where they're living, where they dwell. And then all of these physical functional measures, molecular profiling measures, including methylation clock, all brought together. And get this, there's 50,000 dogs in the dog aging project
So
right
cool.
now. Yeah. So yes, I think we're getting there, thinking outside the box and then just being really clear about what we mean when we use these words. What are the caveats? What is the context? And that way we can all make progress without getting tangled up, in this was seen here, but not there, but here, but not there. The data are always real, right?
Yes.
The interpretation is where things can come a bit loose, but not if you stick to the caveats and the context.
Yeah, getting everyone on the same page, speaking the same language. What I always say is, obviously we come from the stem cell world, which back in the day was the wild, wild west. It's still the wild west, but has formalized a little bit more. I know people have studied aging for a long period of time, but really getting people on the same page, using the same nomenclature, sort of looking at the same things and even describing the same things so you can have a fruitful conversation that works, I think is absolutely important. I couldn't agree more. I know we're moving at breakneck speed and kind of jumping all over the place, but I would love to hear your thoughts. I know you direct an NIH training program. We here at the CREM think that the training of the next generation of great scientists and clinicians is really up to us. Do you have any thoughts at the state of the NIH? Do you think the NIH is going to really back research into healthful aging?
Oh, yeah, absolutely. I mean, look, NIA was one of the later institutions formed, and it's just gone from strength to strength. I have a lot of friends in the Division of Aging Biology. I just love their portfolio. I love what they do, and they work so hard to try and make sure that up-and-coming scientists are taken care of. I served for some years on some of the training branch study sections. I could, it's the joy of these terrific energy, great ideas. We really have to make sure we protect the careers of these early stage individuals. The training program, so this is a T32. We have postdocs and graduate students who come in and they become a scholar of the program. And it's just great because that gives them the freedom. They have, 2-3 years of guaranteed funding, so long as something doesn't go wrong, like terribly wrong. Um, and that gives them a little bit of intellectual freedom. And the award is to them, not to their PI. So they're given this autonomy. You are directing your career to make sure that this aging component is in there and that you're supported. We have a huge mentoring team that feeds in. We have activities. We do twice a year one-on-one meetings, look at your developmental plan, talk with the mentor. Is your biosketch good? Are you getting exposures? Have you been to meetings? What are your papers looking like? And that kind of targeted career advice rather than a workshop, la, 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 tick, 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 and then everyone goes home. This is very much more geared to each individual and plays to their strengths. So that type of intensive training program it's just fabulous. It's a lot of work. I would love to see that be the way graduate school goes, where there's that invested, thoughtful, purpose-built training for all graduate
I
students.
love that idea.
The postdocs do really well on it as well. We have interactions with other T32 programs, one in Seattle, Washington, the other UW, and another at UMN, our neighbors just up the road in Minneapolis. And we have a visiting scholars program. We have a program that we do on campus, bringing in other T32s in biomedical research so that everyone can, strut the stage and show, look, these are the future leaders in biomedical research. And so there are so many opportunities that you can tether to a program like that to just provide opportunities for even more people, not just limited to the ones funded on your own program.
Love it. Absolutely love it. So I know we're both academics, but there seems to be an increasing presence of the commercial sector in aging and longevity. Yesterday, we were at my laboratory and I were at a longevity mixer in which you had massive numbers of commercial entities, but also, investment firms who are actively looking at this space. And we had a discussion about the billions of dollars and the tech entities that may be getting involved. Any opinions there? Is there a place for both academia and the commercial sector to sort of work together? Is it going to be, only accessible, maybe some of these discoveries, only accessible to the super rich? Do you think about those types of potential issues?
Sure. And I've been to a few meetings. So what comes to mind is the Longevity Summit in Dublin.
Sure.
And also the ARDD in Copenhagen. And those are really nice blends of, biotech, commercial interests, and investment and academics. And it's a real melting pot, and it's a great idea. Is there room for everybody? Absolutely there is. Is there a need for money invested in aging research? Absolutely there is. The one caveat I'd say is that the goals, while similar, are not the same. And so I think there needs to be dialogue, also tolerance, and just the willingness to accept that somebody else is going to approach this a little bit differently than you are. So I see all of those things as being vital. I couldn't be more pleased that there are people interested in coming into this aging, research field. And I can tell you, look, there's some just really innovative ideas coming from biotech and from the investment side. I think there's just room for. We won't know until we test. We won't answer the question if we don't ask it.
Yes.
So I think there's a lot of room for everybody in this space. And I think there will be benefits of working together. Absolutely benefits of working together.
And also, I think related to that space, right, and sort of how people are thinking about things, futurists, or, we talked about longevity, escape velocity. Conceptually, the idea of age reversal, right? So that's something that I'm sure you're asked a lot about. I get a lot of crazy emails asking about various things. We talked about in the making of an induced pluripotent stem cell. There's a separate podcast episode we have talking about reprogramming. So at least at the cellular level, age reversal is actually possible. But your former mentor, David Sinclair, obviously is a proponent of maybe epigenetic reprogramming can be used systemically to actually induce age reversal. So forget about delaying the onset of aging-related disease. Do you have any thoughts about contextually the possibility of actual age reversal?
So, yeah, it's really interesting.
Yeah.
So the first time I heard about escape velocity, I thought, well, that's such a bizarre kind of idea. But I started to peel it down and I thought, okay, here we are as scientists. The very pursuit we are engaged in is predicated on the fact that things can be known, that there's a system, that there are interactions, that there are features of these wonderful machines, cells, and the machines within the machines, that this can be known, and how they interact and how they're controlled can be known. So, by the same logic, it should be possible to understand how bodies function. And by a further extension, it should be possible to understand what happens when things start to become go a little bit wrong, when their noise becomes introduced into the mechanisms of keeping homeostasis. So by the time I peel all the way back, I'm less opposed to the idea than I was, right? I mean, as a scientist, you've got to believe you ask the question, you devise a series of experiments, you answer that question, and now you move to the next step. And that step, it could be a nanometer or an angstrom worth of knowledge, but it's a step in the right direction. So I don't know when we would get to that point, but I think as a pursuit, as an idea, as a goal, I have no problem with it.
Love it. And maybe lastly, so that we stay on schedule, something I always like to ask is how your work has sort of been reflected in your own life, right? So, for example, during COVID, we built a COVID test in the center when the hospital was sort of shut down to be able to run sort of COVID tests for our population here at our safety net hospital. During that time, I fed myself and all of my people with chicken nuggets and Coke Zero. That's great, but not sort of great as a lifestyle. So after that, I became vegetarian. So I've been vegetarian for 5 years. So we had this beautiful discussion about metabolism. Maybe you are what you eat, energetics. Has that been reflected in any choices you've made sort of in your life and lifestyle?
Well, yeah, I suppose. Well, I haven't. So I know several of my colleagues are on whatever the pharmaceuticals, anti-aging agents and stuff like that. And I'm not keen on doing anything like that. One thing I did do. So I used to bike to work all year round. I did it for 15 years in Wisconsin. It was pretty hardcore
as well.
Yeah,
yes.
I know.
Wow.
You
Okay.
wear like 2 pants, 3 jackets, 2 gloves, and then get military grade gloves. You get lashicles where your eyes fuse together. It was pretty brutal. And then eventually I said, okay, this is a bit much. So I stopped doing that and drove to work instead. But I didn't stop eating as much as I was eating when I was biking. So a minor adjustment had to be made there, and I imposed that. So I try to match my intake to my output. Now, if I were, an all-year-round swimmer, you're going in the lakes and all that, that's an energetic requirement. So I think the key, and what I do, is try to match my food intake to my expected output. If you're a long-distance runner, you need more food than I do, right? If you were bed rest and very little movement, you don't need as much food as I eat running up and down the stairs after my students telling them to do things.
Sure.
No, I don't. And so I think that matching energy output to energy intake, that is something I certainly have taken on since I gave up the old bicycle.
Yes.
But so that would be about the extent of it. Just trying to make sure that I'm not overeating. And I've always been active. So exercise is important. I think for people in the pursuits like us, there's a lot of thinking going on. It's important to get out of your mind. I don't mean psychedelics.
In the good way.
In a good way. So out, I love being out hiking or outdoors, out in nature, but just getting out and moving around in your space, just separating yourself from the grind of work, I think it's cathartic. Exercise has so many benefits to it, so I do incorporate that, and then trying not to eat more than I possibly should. The size of my pants will remain the same, and so it's the body that has to match the pants at this stage. I know when things are going awry, and make adjustments there, but that's about it. Stay active. I think one of the things that occurs to me, you only get one body. We're only here once, and it's really a flash when you think about it. It's getting faster all the time for me. And you ask yourself, here's this amazing machine that you have that brings your brain and your thoughts around the world so you can experience it. Is this the best you can do? This fuel that you give it, this exercise, this, maintenance are you doing the best for the one body you're ever going to have? And if you start from there, I think, good decisions, come from it. But I'm the last person in the world to tell anyone what to do because I refuse to have anyone tell me what to do. So, I think people know. People know.
Such a great way to end. Appreciate your time. You did a wonderful job with making really complex topics so accessible. Thank you so much for being on the podcast.
And thank you for the invitation. It's really super to be here. Thank you.
We hope you enjoyed the discussion, so please follow our podcast and join me on our journey of understanding and self-discovery as we navigate our way through the fields of longevity, aging biology, regenerative medicine, and the emerging field of geroscience.